Water delivery and pressure systems. Oh my, there's so much to learn. So many pieces of equipment to learn about, so many concepts, so many terms. How do you start? Well, I'm going to help you. I'm going to teach you 43 common topics in 43 minutes. That's an average of just 1 minute per topic. Are you ready? Go! Water sources. A shallow well is defined as a well where the distance from the top of the water, right here, to the pump is 25 feet or less. Now the number 25 feet is significant because this is the number of feet that a standard jet pump can suck water up. It sucks water up like a person would suck water through a straw by creating a vacuum and sucking it right up. Now the theoretical limit for how high you could suck water up is 32 feet. It's impossible to suck water up more than 32 feet. But over 25 feet it becomes very inefficient. So for practical purposes the limit is 25 feet. So a shallow well is called a shallow well because it's 25 feet or less and because you can use this type of pump, a jet pump with a single pipe, you can use that to suck the water up. You can always use a submersible, but most people with a shallow well choose to use a simple jet pump. What I like to call a medium deep well is a well where the vertical distance between the top of the water to where the pump goes is between 25 and 110 feet. This means you can no longer use a standard jet pump with a single pipe, but you can still use a special kind of jet pump which has something called an injector, which has two pipes going down into the water, which creates a flow which pushes and pulls the water up. It's not a very efficient pump, but some people like it because they'd rather keep the pump above the well, above ground, where they can see it, work on it, and easily fix it. It also costs less to buy than a submersible pump. At this distance, between 25 and 110 feet, you have a choice of this special jet pump injector pump or a submersible pump. It's your choice, and that's why I call it a medium deep well, because you have a choice of these two different kinds of pumps. A deep well is a well where the vertical distance from the top of the water to where the pump would normally go is 110 feet or more. Now this figure 110 feet is not carved by stone. Some people think it can go a little bit deeper. But basically over 110 feet it becomes very inefficient to pull the water up from above. So it's really recommended at 110 feet or more that you use a submersible pump which pushes the water up instead of pulls the water up. The submersible pump goes down here under the water. It has a single pipe that goes up. It also has an electrical wire which is attached to the pump, and this electrical wire is attached to your power supply and it is controlled from above. So that's why it's a deep well. It's 110 feet or more, and you can only use a submersible pump. Town water. Town water looks something like this. A water source such as a reservoir goes to a treatment plant which cleans the water, goes to a pumping station which pumps the water into the water tower. The water tower supplies water to the town via gravity. If something goes wrong with the pumping station, there's typically a day or more's worth of water in the water tower so that you could still get water from the water tower while they are trying to fix the problem at the pumping station. So this kind of setup is very dependable. Okay? And in addition, the pump does not have to be as powerful because it can pump water into the tower at an average usage rate rather than having to be designed for a peak usage rate. Not all towns have a water tower. Some go directly from the pump to the house. In this case, service is not as dependable since if something goes wrong with the pumping station, you will lose service. Unless you have a gravity feed system, you will need a pump to pump your water. There are literally thousands of different kinds of pumps, thousands of different kinds of designs. But for our purposes, we will consider four main categories: the deep well submersible pump, the injector jet pump, the standard jet pump, and the centrifugal pump, also known as a booster pump. I will describe each of these pumps in subsequent sections. Every pump has certain characteristics. The most important characteristics are the maximum pressure that it can attain, the maximum flow, that's how fast it can pump the water, the maximum suction height, that's how far it can lift the water from below, and the power consumption, usually in watts, or horsepower. I will discuss all these pumps and all these characteristics in the sections that follow. It is important to know the maximum pressure that a pump can produce. Pressure can be described in one of several ways. For example, if we have a column of water 100 feet, we say that the pressure on the bottom of that column is 100 feet of head. If we can also convert that to meters, and we would say the pressure is 35.5 meters of head. If we look at 1 square inch on the bottom of that column, we would find that it has 43 pounds on each square inch. Thus, 43.3 pounds per square inch, 100 feet of head, and 35.5 meters of head are all equivalent. There is also something called bar, which is very complicated. The best thing to know is that you can just convert to any of these things to bar, or bar to any of these things. If we look at this following page, I have here a bunch of conversions. So you can look at this page to convert any unit to any other unit. It is important to be able to convert any unit to any other unit so that you can use the units that you're comfortable with and compare different pumps that use different units. You can think of flow as the amount of water that passes by a particular point in a certain amount of time. For example, if we were flowing water through this pipe into this bucket, and we flowed the water for exactly 1 minute, and we found out that there was 3 liters in the bucket after 1 minute, we would then say that the flow rate is 3 liters per minute. Now there are different units for describing flow. The 3 most common units are liters per minute, gallons per minute, and cubic meters per hour. Of course, not all pumps use the same units, so you need to be able to convert from one unit type, one flow type, to another. Here is a conversion table to convert from any of the units I described to any other unit I described. This allows you to compare one pump that uses one unit to another pump that uses a different unit. Use the units that you are comfortable with. All pumps come with a power rating. The easiest rating to understand is in watts. When you think electricity, you think watts. Use the power rating to calculate the cost to run the pump. If you use the pump for 1 hour, then the kilowatt hours consumed is equal to the watts divided by 1,000. Not all pumps show you their power rating in watts. Sometimes it comes in horsepower. No problem. Multiply the horsepower by 750. Some pumps just show you an amp rating. No problem. Multiply the amps by the house voltage. For example, if your pump is 7 amps at 110 volts, this equals 770 watts, or about 1 horsepower. Here's a cost example. Suppose in your town the cost of electricity is $0.3 or 30 cents per kilowatt hour. Let's say the pump is 750 watts. That's 0.75 kilowatt hours. The cost to run the pump for 1 hour is 0.75 times 0.3, or about 23 cents per hour to run your pump. I will now describe the relationship between pump power, that's watts or horsepower, and flow and pressure. I will use a bicycle analogy. A fast bike in this analogy is equivalent to high water flow, and going up a steep hill is analogous to producing high water pressure. Suppose you want to hire a man to deliver goods on your bicycle, and you only have 2 bicycles available, this one with a very high gear ratio and this one with a very low gear ratio. If you give this man this bicycle, he will be able to go fast on level ground, but there's no way he'll be able to go up a hill. The mechanical advantage is just against him, and he is not strong enough. If you give him this bicycle here, he will be able to go up a hill, but when he goes on level land, he will go so slow. So what's the solution? Well, the solution is you got to change your ratio. You got to produce a bicycle that has a better gear ratio so that it's a compromise, so you can go both faster on level land and go up a hill. But the problem is this man is weak. He cannot provide the power necessary to go fast on level land, and he can't certainly make it up the hill. He just doesn't have enough power. So what's the solution? Well, the solution is you got to hire a more powerful man. Hiring this more powerful man is the equivalent of buying a more powerful pump. So the conclusion is this: pumps are like bicycles. They have mechanical advantage. If you want to buy a low power pump, for example a 1/2 horsepower pump, you can get such a pump that can produce high pressure, but it will only produce low flow. Or you can get a pump that can produce high flow, but it will only produce low pressure. And if you want high flow and high pressure, you must get a more powerful pump. Let's consider a day in the life of a pump. The number of times the pump goes on and off during the day is called the number of cycles. The total amount of time that the pump is running is called the total pump run time. Now, everyone agrees that excess cycles puts excess strain on the pump. Everybody agrees that long pump runs can wear out a pump. So which is worse for a pump, lots of cycles or running it for a long period of time? Consider this example. You are choosing between two different sets of equipment. You calculate that with one setup you will have 50 cycles a day, but the pump will only run for 1 hour. With setup 2 you will only have 5 cycles a day, but the pump will run for 3 hours. So which should you go with? Well, the answer is, who knows? We don't really know which pump will last longer, and we have to consider electricity usage, noise, we have to consider initial cost. There's so many things to consider. The only thing we know for sure when designing a system is that we want to reduce both the total number of cycles and the total runtime, if possible. Okay, now I will talk about the concept of total dynamic head. Dynamic head is a calculation used to determine the pressure rating of the pump you will need to buy. Dynamic head takes all factors into consideration. Dynamic head is calculated in feet or meters, but can later be converted to psi. The total required dynamic head is calculated by adding up the following: suction head plus delivery head plus friction head plus consumer head plus some extra head. So what does this all mean? Let's get right to it. The suction head is the distance from the water at the top of the well to the inlet valve of your jet pump. Now, if your well sometimes varies according to the seasons, always take the lowest point of the well to the distance to the jet pump. In this case, the suction head is 15 feet. We must know this distance because that distance takes away from the efficiency of the pump. That must be included in when you consider the pressure rating of the pump. So this is called the suction head. Delivery head is the vertical distance from the top of the pump from the pump outlet valve to the destination of where the water is going. In this case, in this example, it's going to a pressure tank. So the vertical distance from this pressure tank to this pump is 10 feet. That is called the delivery head. Friction loss or head loss due to friction is calculated by noting the total distance of the pipe from the well water all the way to the destination, and also noting the diameter of the pipe and the material of the pipe. So in this case, the total length of the pipe from the well water to the pressure tank is 100 feet. The pipe is 1 inch inside diameter and made out of ABS, so we can calculate the friction loss to be 13 feet. Well, how did I do that? From the internet, of course. Go to the internet to find a head loss calculator. Plug in the numbers and it will tell you what the friction loss is. One quick note about this is I tried a bunch of different head loss calculators and they all gave me different numbers. So you may want to try a few before you decide how much your head loss is due to friction. Consumer head is calculated by noting the pressure needed by the consumer once the water reaches the consumer. In this case, the consumer is a pressure tank. That's the final destination of this water. Now, in this case, it's easy to know the pressure that's needed because it's the same as the upper figure of the pressure tank. So in this case, the pressure tank has a range of 30 to 50 psi. So the consumer pressure that's needed is 50 psi. But in order to calculate our total dynamic head, we got to convert this 50 psi to feet. So 50 psi is needed. 50 psi times 2.31, that's the formula to go from psi to feet of head. It's equal to 115 feet of head. So in this example, the head needed by the consumer is 115 feet. In the next sections, I will describe both pump labels and pump curves. If you only have a pump label and no pump curve, then we want to add about 30 feet of extra to the dynamic head because a pump running at its maximum pressure rating has zero flow. So to make sure we have decent flow at the pressure that we need at the house, we need to add some extra so that the pump will produce flow at the pressure we actually need. If we have a pump curve, we can be more accurate. So we don't need to add this extra if you have a pump curve. I'll describe all of this in the following sections. So to calculate the total dynamic head needed, we're going to calculate it in one of two ways, depending on whether we have a pump label only or whether we have a pump curve available to us. If we have a pump label only, then we add the suction head, delivery head, friction head, and consumer head. These are all things we calculated previously. Plus we add an extra of 30, and we come up with a total head of 183 feet, which is equal to 79 psi. So in this case, we must make sure that the maximum pressure on the pump, the max pressure pump label reading, should be at least 79 psi. If we do have a pump curve available to us, we do the same calculation, but we do not add the extra. So in this case, we would come up with 153 feet of head and 66 psi. And we'll use this figure and your desired flow rate and the pump curve to choose your pump. I will go over this in subsequent sections. All pumps come with a pump label. Some things you can not understand, but it's important that you at least understand the four things that I'm going to show you now. Qmax is the maximum flow rate of the pump. In this example, it's 35 liters per minute. Now, this is the flow rate when there's no back pressure on the pump. When there's pressure on the pump, the flow rate will be less. Suction max is the amount of distance that the pump can lift water from below. In this case, it's specified as 8 meters. The power consumption is given as both horsepower and watts, 375 watts and 1/2 horsepower. And this pump can produce a maximum pressure of 35 meters of head, which is the same as 115 feet of head or 49 psi. Now this is the maximum pressure, but with that pressure you're going to have low flow. So if you want to make sure that you have at least decent flow with the pressure, make sure that your pressure, the Hmax of your pump, is at least 10 psi higher than what you're actually going to need. If you buy a cheap, no-name pump, you may not have a pump curve available to you. You may only have a pump label. However, if you buy a good pump from a well-known manufacturer, you should be able to obtain the pump curve from their website. In this case, I'm looking at the Grunefoss JP15 shallow well jet pump, and this is the pump curve that's available from them on the internet. So what does this pump curve tells us? It tells us the flow that we get for any pressure rating. So let's consider the example that we did before where I calculated the total dynamic head when I did have a curve, a pump curve. So what I determined was that we needed a total dynamic head of 66 psi. So we take 66 psi and we note the point right here and we draw a red line to the left until we intersect with the pump curve. Okay, and then we go straight down and we notice that it intersects this bottom line at about 13 gallons per minute flow. And that's pretty good for a house. That's usually more than you need for residential. So we have determined by looking at this pump curve that we have a good pump for our use, the use that we showed in our example. Now, this pump curve will show us the flow at any pressure, any back pressure, but in this case we only needed to calculate that at 66 pounds pressure it would deliver the flow that we needed. Now, suppose we didn't have the pump curve, we would only have the pump label, and the pump label will tell us that the maximum pressure of the pump is 208 feet of head. And using the other figure that I gave you when you don't have a pump curve, I said you need a pump that has at least 183 feet of head. So using that calculation, we would have noted that this pump is okay too. So either way would have worked in this case. Okay, this here is called a centrifugal pump or centrifugal pump. It's one of the oldest designs around and it hasn't been changed in years. It's tried and true. It's very efficient. It's quite cheap and it works quite well. And it's very simple in how it works. Water comes in this inlet valve here. It hits the impeller and gets spun around and shot out the discharge. The only problem with a centrifugal pump, and this is a big problem, is it's not very good at sucking up water. It hates air. A little bit of air in the system and the centrifugal pump will stop working. A booster pump is a pump that's used to pump water when the water is available to the pump and it doesn't have to suck the water up. So if you look at this picture, the water tank is higher than the pump, so it's providing a positive pressure of water into the pump, and it doesn't have to suck water up. It doesn't have to worry about losing prime or air bubbles because the water is always available to the pump. And the centrifugal pump, which doesn't like air, doesn't have to worry in this case, and it can take this water and quite efficiently boost it into this pressure tank in this example. And centrifugal pumps are excellent as booster pumps because they're efficient and they're cheap and they're dependable. So usually when people want to buy a booster pump, they use a centrifugal pump as a booster pump. But a booster pump really just means any time a pump is used in a situation where it's boosting water and doesn't have to suck the water up. Now, if we look at this situation, this is not a booster pump. Even if it's a centrifugal pump, or even if it's called a booster pump, if we're sucking water up, it is no longer a booster pump. So this is a picture of a jet pump. And a jet pump is nothing more than a centrifugal pump with an added attachment called a jet assembly. And what this jet assembly does is it shoots the water round and around inside this chamber in a circular motion using a jet nozzle. And this rotation of the water causes a suction, which is very good at sucking up the water from below. So a jet pump is much better at sucking water up than a centrifugal pump, and it's much more tolerant to air in the line, and it's much easier to get going again if air does get in the line. But it's less efficient than a plain centrifugal pump because it wastes energy in this motion of circulating the water. And some people ask, can a jet pump be used as a booster pump? And the answer is it can be, but why would you? Because it's more expensive and less efficient. Now, jet pumps are good for sucking up water. That's what we just said, right? Does this mean you can just stick the pump in a well like this with a pipe just sticking in and just turn on and it will start sucking up the water like a person sucking Coke through a straw? No, it won't work. A procedure must be followed, and this procedure is called priming the pump. Before talking about priming a pump, I want to talk about a foot valve. A foot valve is a valve that goes on the end of the pipe which then goes into the well. Usually it has a screen on it which is to keep out impurities, but this is not the main function of the foot valve. The main function of the foot valve is to act as a one-way street, so to speak. It lets water in, but it won't let water out. So no water that's in this pipe can escape back into the well. That's the purpose of a foot valve. So when you start up a jet pump like this, when you have a suction, you need to fill up this pipe all the way down to the foot valve. It has to be completely filled with water, and the pump itself has to be completely filled with water, which you get access to the pump itself using this pump priming plug that's located right here. Now in this picture, the only access to this system is through the priming plug. So you would have to pour water into the priming plug all the way down here. And if there was a lot of pipe and it was like a 1-inch pipe and it was a long length, it would take a long time to prime the pump this way through the priming plug. There's actually a better way to do this, and that's with a priming access. That's where you have something like this. You have a valve which is located above the well and above the pump. And that way, when you want to prime the pump, you can open up this valve and simply pour water in, and the water will pour all the way down to the foot valve and stop. It can't go into the well because the foot valve stops it. And it will also go all the way into the pump. Now, the very first time you run the pump, you should still open this plug and pour water in. But after that, you may not have to. You should just be able to pour water in through the access and prime the pump that way. So there is also a pump called a self-priming pump. So does that mean you can just stick the pipe in the water, turn on the pump, and you're good to go like this? Alas, no. The term self-priming pump is a lie. Or if I want to be more polite, it's a misnomer or an exaggeration. A self-priming pump should really be called just prime the motor itself once, and you should not have to prime it again. And it's really quality with close tolerances, so it develops more air suction than a normal jet pump. So it's really easy to prime and less likely to lose prime pump. But that's too long, so what the hell? Let's just call it a self-priming pump. The reason they can call it a self-priming pump is supposedly when you fill this pump with water, it will never lose water. It's designed so that you only have to fill this pump up once. So that's why they get away with calling it a self-priming pump. But really, it's just a high-quality jet pump with better tolerances, and it works better. Now here's the thing. If you have this kind of a setup with no access, you still have to go through this priming plug. So the fact that you have a self-priming pump is not helping you at all in this situation. So that would be stupid to have a self-priming plug if you had no access except through the priming plug. But if you have this kind of a situation, you probably don't need a self-priming pump either, because it's easy to prime the pump through this axis. So I'm not exactly sure why you need a self-priming pump, but people say it's a lot better quality and it's just a lot easier to prime the pump and much less likely to lose prime or to stop working because of air pockets. Okay, so this is a deep well jet pump, and it has the two pipes going down into the water, and it has a foot valve on the bottom and a thing called a jet nozzle and a venturi over here. And what happens is it creates this circular flow of water like this, and the circular flow of water causes a suction which brings up some additional water up. So if you look at like a standard jet pump and you look at this part, what they've done is they've basically taken this part and they've elongated this section here and this section here become the two pipes, and they've put the nozzle and the venturi into the well. Conceptually, this is how it works. Imagine that you took a garden hose and shot it up a pipe underwater. That would shoot the water out, but would also draw in water from the surrounding area. So that's the way that this deep well jet pump works. But my question is why? Why would you want this? This kind of pump is extremely inefficient because most of the energy is in creating the circular flow of reusable water that isn't really being used, that isn't really being pumped. It's just water that's circulating over and over again. And so only a little bit of water is being drawn up. And this might be like 10 times more inefficient than a submersible. So I'm not sure why you would want this. Maybe you just don't like the idea of putting a pump underwater. Maybe you want to see the pump. Maybe you don't care about the cost of electricity. I'm not sure why you would want this pump, but people buy them, so there must be a reason. Okay, so here's a picture of a deep well submersible pump. It really can go in any well, but they call it a deep well submersible. It's about 4 inches wide, a couple of feet long, and it's waterproof and goes underwater. It's very efficient because it pushes the water up instead of pulls it. It has a wire that goes up and is controlled usually either by a pressure switch or a float switch or a variable frequency drive. It's efficient, it's dependable, it's good. The only problem is it's usually much more expensive than a jet pump. A water storage tank is not the same as a pressure tank. A water storage tank is only used to hold water. A water storage tank comes in a variety of shapes, sizes, and materials. For example, here's a stainless water tank, and here is one shaped like a wall. Pretty cool, huh? Now, it has a variety of uses, a water tank does. For example, here's a water tank being used with a town system, and this town water we're going to assume is not dependable and or the pressure is too low. So when the town water is available, it goes into this large water storage tank. If the town water becomes disrupted, you still have all the water in this storage tank, and from the storage tank it goes to the house via this booster pump. Even if the electricity goes out or the booster pump breaks down, you still at least have water available to you through this faucet on the side of the water storage tank. A water storage tank can also be used in a well system to make the well system more efficient. For example, the submersible pump in this case can go directly into a large water storage tank, which means it doesn't have to cycle that much because it doesn't go off until the tank gets all the way full and doesn't go on until typically the tank is at least half empty. In this situation, you can also buy a less powerful and cheaper submersible than you otherwise would, because you only need enough pressure to get the water into the storage tank, and the remaining pressure that's needed by the consumer is given to you by the booster pump. There is also something called a float valve. This is used to control the water entering the tank when there's a continuous flow of water available to the tank. When the tank is full, it shuts off the water. When the water level starts to go down, it lets water in. It's basically working the same way as what you're used to seeing inside a toilet. There is also something called a float switch. This goes inside the water storage tank and determines the level of water inside the tank. When the water goes up to the top, the switch is turned off, which turns off the submersible pump. When the water level drops, this ball goes down and turns on the switch, which turns on the submersible pump. There are many styles of this switch. This is an old-fashioned style. They also have more electronically based styles now. There are 3 kinds of pressure tanks: stainless, bladder, and diaphragm, and they come in a variety of sizes and materials, but what they all have in common is they mix water and compressed air together to create pressurized water which can then be used by the system. Now, pressure tanks have been around forever and probably will be around forever because they are the best way to solve a certain problem. And nobody has figured out a better way to solve this problem than by using a pressure tank. So what is that problem? Let's first look at a system without a pressure tank. So here we have a storage tank connected to a booster pump connected to your house. Now notice that every time you use the faucet, the booster pump is going to go on. Every time you flush the toilet, the booster pump is going to go on. So there's going to be many cycles of this booster pump going on and off. In addition, the booster pump is going to operate very inefficiently because you might be using water at this faucet at only 1 gallon per minute, and this booster pump is capable of 10 gallons per minute, so it will only be operating at 10% efficiency when you're only using 1 gallon per minute. Now if we add a pressure tank into the system, and if it's a fairly large pressure tank, let's say, then what happens is water will go into the pressure tank until it hits 60, and then the pump will go off. And then the system will use this pressurized water until the pressure goes down to 40, and it will be able to use the pressure tank many times to wash your hands, to flush the toilet before the pump has to go back on again. And in addition, when the pump does go back on, there's no restriction in how fast it can go. It can pump water into the tank as fast as it can, so it's very efficient in pumping the water back into the tank. There are several pieces of equipment that are normally associated with a pressure tank, namely a pressure switch, a pressure gauge, and somewhat less often, a relief valve. And these items can go anywhere along the pressure line or even on the tank itself if there's an access point into the tank. So what is a pressure switch? It usually comes at a preset range like 40 to 60, and it monitors the pressure in the system. And if the pressure goes below 40, it turns the pump on. And if the pressure goes above 60, it turns the pump off. And so it's the pressure switch that maintains the correct pressure inside the pressure tank. Now, a pressure gauge is visual confirmation that the system is working correctly. You don't really need a pressure gauge, but it's very useful because you can make sure that the pressure is what it's supposed to be. Now, a relief valve is useful when the maximum rated pressure of your pump is higher than the maximum rated pressure of your tank. You don't want your tank exploding. So what happens if the pressure switch, for example, failed and the pump kept on pumping, it might explode the tank. So what a relief valve does is it's set to a certain pressure, like 60 pounds, and if the pressure goes above 60 pounds, it lets water out of the system. As I mentioned before, there are 3 types of pressure tanks, so let's get into that now. The first type of tank I'll talk about is the old-fashioned stainless steel tank. This kind of tank has been around forever. Basically, it's completely hollow, and the way it works is that when the tank is empty, there's 0 pressure in the tank. As it starts to fill up with water, it compresses the air above the water. And at a certain level, like right here, it gets to be 40 psi. And as it continues to rise, the water, the pressure gets higher and higher until it reaches 60 psi, which is the cutoff pressure. So if this is attached to a pump and a pressure system, what happens is the water goes up to here, 60 psi, it goes off, the pump goes off, the system uses the water until it goes back down to here, 40 psi, and then the pump goes back on. So the water goes up to here, down to here, up to here, down to here. Now the thing to notice about this kind of system is that compared to the size of the tank, you have very little bit of pressurized water. You look at the tank and you think, gee, it's huge, I should have a lot of pressurized water, but you don't. You only get a little bit of pressurized water. And for this reason, some people don't like this type of tank because they want something that's more space efficient. Other people don't care. Maybe they live on a farm, they have a big house, a big basement. They don't care if the tank is big. The other thing to note about this kind of tank is that the air and the water are touching each other, which it creates a situation where there tends to be a loss of air pressure over time. So every once in a while you have to do maintenance on this tank, and I'll talk about that in a second. Now here is a real-life picture of a pressure tank. Now when you set up a pressure tank, you have to set it up with a bunch of valves so that you can do maintenance on the pressure tank. So for example, if you find that you have a loss of pressure, you turn off the pump, you close this valve, you close this valve, you open this valve, you open this valve, and you let all the water drain out of the system. Then you set the valves back the way they're supposed to be, and you turn on the pump, and then you've reset your pressure tank, and that should be good for another 2 months or so. So this is a picture of a bladder tank. Now a bladder is basically a heavy-duty balloon, and what happens is when water comes into the system, it fills up this balloon with water, and the air above the balloon gets compressed. When you want to use the water, the compressed air pushes down on the balloon, and the water shoots out of the system. Now there's a couple of advantages to this over the stainless. First of all, the air and the water never touch each other directly. They're separated by the bladder, and therefore you don't tend to lose air over time as you do with the stainless tank. The other advantage of this kind of tank is that when the tank is empty, you don't have a pressure of 0. You fill up the tank to a starting pressure of 38 pounds, which is 2 pounds less than the cut on, and that way as the water starts to fill up, almost immediately you're getting a pressure above the cut on pressure. And so what happens is the tank is able to create more pressurized water compared to the size of the tank. A higher percentage of the tank is used to hold pressurized water than you do get with the stainless. So it's more space efficient than the stainless tank. Here's a picture of a bladder tank, a real life bladder tank. And notice that it has this flange here. So that's where the bladder goes. And in some tanks like this one, you can actually replace the bladder if it breaks or deteriorates over time. Well, that's if you can find the part. Good luck with that. So this is a picture of a diaphragm tank, and a diaphragm tank is really very similar to a bladder tank. In fact, it behaves almost identically. The only difference is instead of having a bladder or a balloon, it has a single piece of stretchable rubber that goes across the middle of the tank, which is called a diaphragm. Now this diaphragm is set into the tank at manufacturing time, and it cannot be removed, it cannot be adjusted or anything else. It's just fixed. And the tank is totally sealed. Now the people who like this kind of tank, they say that it's higher quality than the bladder. But the problem with this kind of tank, and here's a picture of the tank, is there's no access to the inside of the tank. So if something ever goes wrong with the diaphragm tank, you just got to throw it away. So that's my overview of pressure tanks. If you want to learn more about pressure tanks, I have another video about pressure tanks. This is one of my most popular videos. It has 361,000 views, and it tells you everything you want to know about pressure tanks. I'm going to talk about some common configurations. So here's a configuration where you have a well pump going directly to the pressure tank in the house. And it's controlled by a pressure switch, which then has a wire that goes all the way down to the submersible and turns the submersible on and off so that the pressure inside the tank has a range of, let's say, 40 to 60. Now, the thing about this kind of setup, there's nothing wrong with this setup, but if you're going to have this kind of setup, you should have a large pressure tank so that you don't cycle too often, because if you have a small pressure tank, you're going to cycle often, which is not going to be good for your submersible pump. And the other thing to note in this kind of situation is that you're going to need a fairly powerful submersible pump, especially if this is a deep well, because not only do you have to push the water all the way up the well, but you also have to fill the pressure tank, which is an additional 60 pounds. Here's an alternative to the previous example. In this example, we have a submersible pump going directly to a water storage tank. And notice that this water storage tank has a faucet on it. So in the worst case, if everything fails, you still can get water from this faucet. Now this water storage tank is controlled by this float valve, and from the water storage tank, we use a booster pump to go to the pressure tank. The booster pump is controlled by this pressure switch here. Now I actually think this is the better way of doing things. It has a number of advantages. First of all, the submersible pump does not have to be as powerful because it only has to pump water to the storage tank. It doesn't have to fill the pressure tank itself. In addition, there can be many less cycles of the submersible pump because it's only going on when the storage tank is almost empty and going off when the storage tank is full. And if the storage tank is big, that means there'll be very few cycles of the submersible pump, which will greatly increase the life of your submersible pump. For this part of the system, we have a cheap and dependable booster pump, and it's easy to work on. If something goes wrong with it, it's easy to fix, it's easy to replace, and so I think this is the better way of doing things. This is a diagram of a system with a variable frequency drive controller. Notice that there is no pressure tank. The variable frequency drive controller monitors the pressure in the system with this pressure sensor. And when it determines that water is needed, it turns on the submersible pump. And when it determines that no water is needed, it turns off the submersible pump. In addition, the VFD can control the actual speed of the motor so that it provides a constant pressure. So you set the pressure you want, like 50 pounds, and it will vary the speed of the motor so that you get exactly 50 pounds of pressure. In addition, it has something called soft starts and soft stops. This means that every time the motor goes on, it starts it up slowly, and when it turns it off slowly. This is supposed to increase the life of the motor, they say. So it has a lot of advantages. The main disadvantages are that every single time you turn on the water, you're going to turn on the pump. Well, is that a disadvantage? At least you don't hear the pump because it's in the well, and they say with the soft starts and soft stops, the pump will still last a long time. The other disadvantage is if something goes wrong with the system, there's no extra water available. There's no pressure tank, there's no storage tank, so when the system dies, immediately you have no water. So some people don't like it for that reason, or they don't like the fact that you're dependent on this electronic device. But other people like the advantages of this system. It's really up to you. In this example, you have your well pump going into a large water storage tank that is above the height of the house. And this is called a gravity feed system. In this example, you don't need any pressure tank or any pump because the water can be delivered to the house simply by gravity, by flowing down these pipes. So this system has a number of advantages, namely that you don't need any pressure tank, you don't need any pumps here, and if something goes wrong with the well system, you have quite a large supply of water which will still be available to the house. But the main disadvantages of this kind of system is you won't get a lot of pressure. For example, in the best scenario, when you're going from the top of this water tank to the bottom faucet here, you might get 30 feet of pressure. 30 feet of pressure is only equal to about 13 psi. If your pressure tank was almost empty and you were going to the top faucet, you might only have 10 feet of water, and that would be only 4.3 psi. So the main disadvantage of this kind of system is insufficient pressure. In a second, I'm going to be talking about a hybrid system, but before I do that, I have to explain what a check valve is. A check valve is a valve which allows water to flow in one direction. For example, if the pressure on this side is higher than the pressure on this side, the water will flow like this in this direction. But if the pressure on this side is higher than the pressure on this side, it will not allow the water to flow in this direction. This kind of check valve here that I'm showing this picture is a gravity check valve. It has a little flap like this, which is in the inside of this, and so it has to be mounted in a particular position so that the gravity works. There's also something called a spring check valve, which works with the spring principle so that the check valve can go in any direction at all. Now, a check valve is sort of like a foot valve, which I explained before, but it goes in the middle of a pipe. So a check valve in this picture goes in the middle of this pipe and it allows water to flow in this direction, but it doesn't allow water to flow in this direction. This is an example of a hybrid system. It has a water storage tank located above the height of the house, but it also has a booster pump. In the normal situation, it will use the booster pump to provide high pressure water to the house. Water will come down from the pressure tank, go into this system, and will be pressurized and go to the house. Now this check valve will prevent the water from going back up in the wrong direction back into the water storage tank. Now, if this pump were to fail, for example, suppose the electricity goes out, well, at first there would be some pressure here. So when you turn on the faucet, it would use the pressure from this pressure tank. But as the pressure from here kept on dropping and dropping because you're using the water, eventually the pressure from this water storage tank would be higher than the pressure down here, and that would cause the water to flow through the check valve to the house. So this is a hybrid system. It has pressurized water when everything is working right, but allows you to have gravity when there's a problem with the electricity or something like that. Okay, well, that's it. That's my video. That was a lot of work. I hope that gives you an overview of a bunch of different topics. Of course, there's not enough detail here for you to become an expert in any of this. You'll need to delve further into these individual topics if you want to actually use these systems. But I hope I gave you an overview and just introduced you to a number of terms and equipment, and I hope that will help you get started. Thanks for watching my video.